All right, so it says a spring oscillator. This is 57. If we start with just talking about period, for a pendulum, that's 2 pi times the root of L over G. And for a spring mass system, that's 2 pi times the root of M over K. Of all the things that are here, does anything that's related to the pendulum or the spring mass change when you take that system up to the moon? We can go through each thing. It's like, will the mass that I bring with me change when I have it on the moon compared to the Earth? No. Mass shouldn't change. It is a measure of how much matter there is. So if I take something of mass 20 kilograms, it should still be 20 kilograms on the moon. How about the spring constant of a spring? Will the spring constant of a spring change? That's determined by the material it's made out of and how tightly coiled it is and all that kind of stuff. Will any of that change on the moon? I don't think so. The length of a string. Will the length of a string change when I take the pendulum to the moon? Unlikely. Will the acceleration of gravity change? Will the acceleration of gravity be different on the moon than it is on the Earth? Yeah, most certainly. So for us to do this, we probably should figure out what the acceleration of gravity is on the moon. Now, I know that we could just look it up. So we should. I do want to remind you that we talked about what it would take for you to calculate it. And so if we want to just have a little reminder, force of gravity are these things. This is first semester, so it's a long time ago. If I'm trying to find the acceleration of gravity on another planet, I act like I'm standing on the other planet. I cancel out my mass on the other planet, and this gives me the acceleration on the other planet. In this case, I would need the mass of the moon, thus m for mass of moon, and r squared would be the radius of the moon. So that would be how we could figure out what this is. Of course, if I don't know the acceleration of gravity on the moon, I probably don't have its mass and radius memorized either. So I'm going to be looking up something one way or the other, right? And I mean, probably most of you don't have this memorized. There's no real good reason to have that memorized either. So probably would do just as well just to find out what the acceleration of gravity is on the moon. So you guys have access to incredible computing devices. I will leave that task to you for a moment. Really? I'm sorry. We're not going to do this for very long, so. I don't know what it is. It's like 1/6 of the Earth, though, so 1.6. Okay. Now, the question is a little more obtuse than this, so let me remind us. Determine the ratio of their periods on the moon. So they have equal natural frequencies on the Earth. Determine the ratio of their periods on the moon. So if they're equal, the ratio of this one isn't going to change. The ratio of this one is. Now, this is a weird question. The ratio on the Earth is 1 because they have the same period. We need to see by how much the ratio changes for the one on the moon. Let me think of what would be best. I think the best way probably to do this. Such a weird question. So here's how I would do it. I think it will be easiest for us. We just need to figure out how much this one changes. So they don't tell us what the period is. So I'm going to pick a period, something easy. Let's say the period is 1 second. That would be 1 second on the Earth. That okay so far? Now, I'm doing that because that means pretty easily that the period of the pendulum to the period of the spring will be 1. They say they have the same natural frequency on the Earth. This one's not going to change on the moon. It's still going to be equal to 1. I want to find what the period is for the pendulum on the moon. To do that, you need to figure out something about this that we can use on the moon. You need to figure out what the length of that pendulum is. That way we can use that to calculate what the period will be on the moon. I'm going to leave that right now for you because I found out in first period there's a lot of interesting answers here. So I want you to take a moment and figure out what the length of a pendulum would be that would oscillate with a period of 1 second. This is a cuckoo clock. You could hang it on a wall. And I want everybody to do this because I saw some weird stuff in first period. So we should all get the same number here. Use 9.8. And I'm going to come and look at your work. So if you don't know what I'm asking you, I'm asking you to solve for the length of a pendulum that would have a period of 1 second on Earth. That the length of this pendulum is 0.25. We can figure out how that's going to be affected by going to the moon with this pendulum. So on the Earth, this pendulum would have a period of 1, and therefore the ratio would be 1. On the moon, we're going to have a different acceleration of gravity, so we need to find the new period on the moon. So .25 divided by 1.6. So I'm dividing by a smaller number. I'm going to expect this period to be substantially different. Less gravity. It's going to take longer to oscillate. So this should be an all skate. I will select one of you in just a moment. .48. So my new ratio is going to be 2.48. Because we picked 1 second as our starting one, our ratio is just going to be based on how much the pendulum's period changed. So it was 1 to 1 before, now it's 2.48 to 1. So, kind of a silly question. I think they could have probably gotten this out of you a different way. That would have been just as effective at talking about what changes and what doesn't. I think putting the ratio in there made it more cumbersome than necessary. What other questions on the homework would you like me to talk about? Kate?
41.
Now, I worked on number 41 in first period, and I think there's the potential for a trick question on the AP exam by looking at this one. So I think it's worth kind of talking about. So the trampoline is to be treated like a spring mass system. That's my assumption. So when the kid stands on the trampoline, I should probably make that a little bit more pronounced. There. When the kid stands on the trampoline depresses 10 centimeters. And the first question they ask is, what is the spring constant of the trampoline? So I'm reminded that if it's like a spring, the force from a spring equals kx. The minus sign reminds me that it's the direction. So if the trampoline was pushed downwards, it'll apply an upward force to the thing that pushed on it. So when they come to equilibrium, when the person stands on the trampoline and they come into equilibrium, their downward weight will be balanced by the upward force of the trampoline. It is that ratio that, it's that balance that allows me to figure out what the spring constant is, because I can set the net force equal to 0 from that. So from here, I simply say that kx minus mg equals 0, or kx equals mg. They tell me the mass of the kid is 60, and that the trampoline was depressed 0.1 meters. So k times 0.1 equals 60 times 10. So I think that gives me a spring constant of 6,000 newtons per meter. That's part A. Now, the next part of the problem is where I think if I were worried about your performance on the AP exam, where I would probably say that there's potential here for some AP exam trickery. They pull the person down an additional 5 centimeters and set them into vibration. So the first thing they wanted was, what is the frequency of that vibration? I don't think that part's too big a deal, because frequency is equal to omega divided by 2 pi, or 1 over 2 pi times the square root of k over m. This has nothing to do with how much they were pulled down and released. So I'm not worried too much about this question. As long as I have the spring constant right, I think I can get the frequency straight away. I think some of you will struggle to get the spring constant because, again, you're dividing by 2 pi, and we've seen what kind of havoc that can wreak. So be careful. When I look at this, 6,000 divided by 60 is 600. It's 100. Square root of 100 is 10. This is 10 divided by 2 pi. So I'm thinking my frequency is just a little over 1. So when you're doing your calculator work, be careful. We've seen this before. 1 divided by 2 pi makes you guys crazy. So I'm not really concerned about what this answer is. I don't think this one's all that tough. I think it's the next question that's tough. You have to read it carefully. The next question says, when the strap is released, what are the energy and frequency of the boy trampoline system? What assumptions did you make? Frequency, pretty straightforward. I made no assumptions except that it's a spring mass system. Energy, that's a tough one. And let me explain all the reasons why I think that's a tough one. Can I erase the frequency stuff? Here's why I think we have a problem with the energy one. If I pull the spring mass down an additional 5 centimeters, how much energy is actually in the spring? If this is the energy in the spring, do I put 5 in for X, 0.05, or do I put 0.15 in for X? That's the first thing you might be wondering. And the answer is not as obvious as you might like. There is energy in the trampoline before it starts oscillating. But remember, he's not an oscillator then. He's not moving. Because of that, the amount of additional energy in the system is only related to how much more the trampoline is pulled down. That is the additional amount of energy. But that's not even the part I'm worried about. You know, they lost gravitational potential energy. Right? They are lower than they were before. That is a change in height. So although they gained this energy, they lost this energy. What are they really asking in the question? Now, they are specific, but they could be specific in another way on the AP exam. They say how much energy is in the kid trampoline system. So they're asking only for this. But if they asked how much energy was in the system, you probably have to do both. Do I think the AP exam is going to expect you to know that? Yeah, I'm afraid so. How many times have we looked at problems and they specify things like the human Earth system or the box Earth system? Have we seen that a few times? So I'd be careful. The change in height is a change in gravitational potential energy. So I don't know. I know that in this problem, they are only looking for this answer. So what assumptions did you make is also asked. The only assumptions we made is that it's a spring mass system. So what other questions do you have? Is there anything else that we have not yet discussed that you would like to ask? Yes, Kyle. Can I go over 21? Yes, I can do this one. So 21. A spring with a spring constant of 1,200 per meter has a 55-gram ball at its end. If the energy of the system is 6 joules, what is the, and then they ask a whole bunch of questions. So let's just get a quick little picture here. So the spring is 1,200 newtons per meter. The ball is 0.055 kilograms. I am aware that I have to put everything in kilograms, or I have to put it in grams. The spring constant is in newtons, and that's kilograms. That's why I'm going to convert the ball to kilograms as well. They tell me the system has 6 joules of energy. That's also kilograms. So yeah, ball has to be in kilograms if I want to do this problem. So they are specifying something about the energy. I know that if I have the energy, I could probably figure out the amplitude of the system. because they told me the spring constant. So I see a direct pathway to figure that out. I don't want to plug everything in unless you want to see the mathematics of it. But do you see that you can get X max from here? Because we have K and we have the energy. I will continue. I'll do the problem if you'd like. But yeah, so you're right. 6 equals 1/2 1200 X max squared. So I can figure out the amplitude. I can also figure out the frequency, because I think they asked for frequency. Oh no, that's what is the amplitude that it vibrates at. So they didn't even ask for the frequency. I could figure out frequency though. I'm saying it because I'm trying to think of all the different things that could be asked. And since I have the spring constant and I have the mass, I can figure out the frequency. Now, I don't need any of those things to figure out what the maximum speed is. They told me the total energy. That total energy needs to stay in the system even when we're talking about kinetic energy. So when all that energy is kinetic energy, I can use that to find out what the maximum speed of the ball is. I'm pretty sure that's what they're asking. What is the maximum speed of the ball is part B. Now, question C, what is the speed when the ball is in position A/2? Now, in order to get that, we need to figure out how much energy the ball has when the ball is in that position. The total amount of energy is 6 joules. That's true. But the energy is spread out in 2 places now. In this problem, this is now half of the amplitude. Now, you could do this way. You could plug in whatever you got for X max here, and you could work the problem out. But we did a similar problem to this yesterday. And in that similar problem, we found that this is 1/4 of the total energy. Because that A/2, when you square that 2, you get 1/4. So it's 1/4 of the total energy, which means that 3/4 of that energy has to be there. So we could just say 3/4 of 6 equals 1/2 mv squared. You could do it that way. Or you could just solve this for v here. Your decision. It doesn't make any difference to me. Both of those methods will work just fine. And that's it. That's the end of question number 21. Does that answer your questions? All right. Is there anything else I can speak to? Yes, ma'am. Now, I want to stop for just, but the energy in a pendulum is based on how high it swings. And in this example, it's going to hit that peg, and it's going to change the way it swings, but it should still swing to the same height. So it does something like that, hitting the peg and doing that. So now, this is mgh. That's the energy in a pendulum. It's gravitational potential. But h is a little tough to calculate. It's like, that's h. Now, I don't know if you remember, but we talked about finding out H in terms of theta and L first semester. We did conservation of energy. It's been a long time, and probably some of you don't remember that. It looks like that. It's a whole triangle thing. If you don't remember that, you could be forgiven. But I would like you to know where it came from, because it does show up. And there, I'm drawing. This is L, and pulled it back theta. Can everybody see what we're looking at right here? I'm looking at two positions, straight down and pull back to here. Okay? That's what I'm comparing. This green side from here to here is the adjacent side of a triangle. Do you see the triangle that I'm trying to point out to you? Right angle here, hypotenuse here. So cosine of theta would be this adjacent side over L. That okay? This is H right here. Do you also see that H plus A has to equal L? Can everybody see that okay? I need to know before I go on. We're following along. What's that? Bianca, there's a chair right here. Okay, just want to point out, there's lots. But if we're having trouble seeing it, I'm trying to look at this triangle right here. Do you see this triangle right here? Okay. I can't hear you. Okay. I'm not sure how far to go back. I took a pendulum like that, BB8, and I pulled him back, and I'm comparing how high he is here to where he started from. Are we okay with that? So when it was pulled back to here, I just drew a perpendicular line right here. So all I tried to do was find the perpendicular. That way I can make a right triangle. That's all I've done. And I said that this side would be the adjacent side because it is next to the angle. Is that okay? And then I said that the cosine of that angle should be A over L. Is that okay? All right. But all of this whole string from here all the way here is still just L. So how much higher it is got to be related to this value for A. Would you agree? So H plus A is equal to the whole length of the string L. Is that okay? It's all right. I look, you understand, I am desperate for you guys to understand things. I'll take whatever time it takes. So I'm just going to take this guy right over here and write that as A equals L cosine theta. And then I'm going to drop that bad boy in right there. So we get H plus L cosine theta equals L. And all of that, because I need to say that H equals L minus L cosine theta. That's this guy right here. Now, I know you might have no idea why I'm doing all of this, but I do have a goal. It's not a great goal, but it's to show you that the energy in a pendulum can be related to the angle and not the height. This can show up on the exam. We're going to play around with this after your test a little bit because we kind of didn't talk as much about pendulums as I need to. Now, I still want to answer the questions that are posed here. So am I good so far? So there's another question that I need to kind of talk about. And it says, derive the expression for the, oh, I'm sorry. I never explained this.